So before I start today's class, I'd like to take you on a trip that I recently did to share some of the things that excite me in my life with all of you. I actually went to Washington, D.C., and the highlight of the day for me was to visit the National Museum of American History. Some of you might know this. In 1998, a team led by Wolfram Burgert and myself put a robotic tour guide into this museum. This robot was in the museum for about 2 weeks, and it led kids and visitors of the museum through the exhibit. It did localization, similar to what I taught you before. It used a learned map of the environment. We programmed by hand the specific location of exhibits, and the robot was able to say something. It was also able to smile and to frown, and as you can see in this video, sometimes even kids climbed onto it. But today I'm here to see Stanley. Stanley has been here for a couple of years now on exhibit, our robot that won the DARPA Grand Challenge. And it was really fascinating to see the thing that we've built and visited in its own little room in the Smithsonian Museum. This exhibit has been made specifically to celebrate Stanley's victory. And in exploring this exhibit again, I found that the curators had actually put some program code on the wall for people to understand. And as I zoom in, you can see Kalman. So at the time, we are already working with Kalman filters. And in our parameter file, as shown here, the word Kalman occurs many times. So what I've been teaching you in last class about Kalman filter really had a major role to play in making Stanley the robot win the DARPA Grand Challenge. So these are really deep emotional moments for me, going back to the past and seeing what we've done and how it's being preserved. But I wanted to share this with everybody here. Because it's part of my life and it's part of what we've done in building self-driving cars. And the methods I'm teaching you in this class are essentially the same methods as we used back in Stanley and in Junior when we did the Urban Challenge.
How cool is Stanley? One of the most amazing things about self-driving cars is being able to move between the world of bits, which is the computer code we write, and the world of atoms, which is the car that our code ultimately drives. One of the amazing things about Udacity is that we have our own self-driving car. Her name is Carla, and in some ways she looks a little bit like Stanley. They're both off-the-shelf cars with lasers, radars, cameras, and computers. At the end of the Udacity Self-Driving Car Engineer Nanodegree program, students form teams and write code to actually drive Carla in the real world. Think about how amazing that is. A student in one part of the world works with a student in another part of the world and partners with yet another student somewhere else in the world. They write code that drives a car in a simulator, then they send it to Udacity where we test that code in the simulator as well. And when everything works, we put their code in a car they've never actually seen, and it drives around a track and even negotiates a traffic light. I hope you join us in the Nanodegree program and get a chance to run your code on Carla too.
So in this class, we will learn about particle filters. In our sequence of algorithms for estimating the state of a system, this is the third one. And in many ways, it's the best one. It's the easiest to program, and in most ways is the most flexible. And to understand why I'm saying this, let me start with a little quiz that goes back into the first two classes. In class 1, we learned about histogram filters. In class 2, about Kalman filters. And we even had a proof there. Today, I teach you about particle filters. But you can't really know about particle filters quite yet, so my questions will only pertain to histogram filters and Kalman filters. First, I'd like to know whether the state space was discrete or continuous. Please check exactly one of those two boxes over here. And I understand these are not entirely non-ambiguous, these questions, but in the spirit of the method, please check whichever fits best. Well, the histogram filter was discrete. The distribution was defined over a finite set of bins, whereas the Kalman filter had a continuous state space. So let me ask you a second quiz. In particular, I would like to know whether the distributions that can be represented may be unimodal or can also be multimodal. So check unimodal, if this is all we can do. Whereas if we can have multiple bumps in our posterior distribution, check multimodal. And here the histogram filter scores better. Even though it was discrete, it was able to represent multiple bumps, which the Kalman filter couldn't, so it's unimodal. If you forgot this, go back to the past class and look at this. The Kalman filter was a single Gaussian, which is by definition unimodal, whereas a histogram filter can have bumps over arbitrary grid cells. The next question I didn't need to dwell on in the class, but I think it's important. When it comes to scaling in the number of dimensions of the state space, the amount of storage we have to assign, I give you two answers. It could be quadratic or exponential. So we have quadratic, exponential. And I understand I didn't really discuss this, but go back in your memory to how grids are represented and how Gaussians are represented. And I promise you, one of those answers is correct for either of the two filters here. The histogram filter's biggest disadvantage, it scales exponentially. And the reason is any grid that is defined over k dimensions will end up having exponentially many grid cells in the number of dimensions, which is really misfortunate because we can't really represent high-dimensional grids very well. So it works really well for low-dimensional problems, like three-dimensional robot localization problems. The Kalman filter, in contrast, under certain assumptions, is quadratic. All we represented was a vector, the mean, and a covariance matrix. And the covariance matrix is quadratic. And it turns out all the computation, if your measurement space is fixed size, ends up to be quadratic without a proof here. So you just have to take it by faith. But the key thing is, this is a much more efficient method. So if you have a 15, 20-dimensional state space, the Kalman filters will be more efficient than the histogram filters. Let me ask a last question. When applied to robotics, do we believe the histogram filter is exact or approximate? Same here. I know we never talked about this. Please just check the boxes you find most likely and then move on to see my explanation. Well, histogram filters tend to be approximate because the world tends not to be discrete. So in localization, for example, it's clearly an approximate filter. It turns out Kalman filters are also approximate, and that's a much more subtle observation. It turns out Kalman filters only are exact for linear systems, whereas the world happens to be nonlinear. Now this goes into a lot of deep math, which I don't want to get into here, but you should understand that both of these filters are not exact. Both of them tend to be just approximations of the correct posterior distribution. Now let's look into particle filters, the subject of today's class. And it's really interesting to see the answers for particle filters. First, the state space for particle filters is usually continuous. So we can deal with the more interesting version of state spaces. But we're not confined to unimodal distributions. We can actually represent arbitrarily multimodal distributions. They are also approximate, just like the other two filters. And in terms of efficiency, the word is still out there. In certain incarnations, they clearly scale exponentially, and it's a mistake to represent the particle filters over anything more than, say, 4 dimensions. But in other domains, mostly in tracking domains, they tend to scale much, much better. And I've not seen a good treatment yet of the complexity in practice for particle filters. However, the key advantage of particle filters is actually none of those things over here. The key advantage, at least in my life, has been they're really easy to program. As you hopefully see today, writing a particle filter is really, really easy. In fact, you will write your own particle filter for a continuous valued localization problem, which is in many ways more difficult than any of the problems we talked about before. So let's dive in and see a particle filter in action. So here is a floor plan of an environment where a robot is located, and it has to perform what's called global localization, which is it has no clue where it is and has to find out where it is just based on sensor measurements. This robot has range sensors, as indicated by the blue stripes. Those use sonar sensors, which means sound, to range the distance of nearby obstacles. And it has to use these range sensors to determine a good posterior distribution as to where it is. But the robot doesn't know it's starting in the middle of the corridor. In fact, it is completely uncertain as to where it is. Now the particle filter represents this using particles. Each of these red dots, of which there are several thousand here, is a discrete guess where the robot might be. It's structured as an x-coordinate, a y-coordinate, and also a heading direction. And these three values together comprise a single guess. But a single guess is not a filter. It is the set of several thousand of such guesses that together comprise an approximate representation for the posterior of the robot. So let's start the video. In the beginning, the particles are all uniformly spread, but the particle filter makes them survive in proportion of how consistent one of these particles is with the sensor measurement. Very quickly, the robot has figured out it's in the corridor, but two clouds survive because of the symmetry of the corridor. As the robot then enters one of the offices, the symmetry is broken and the correct set of particles survive. Let me play this again. The essence of particle filters is to have these particles guess where the robot might be moving, but also have them survive using effectively survival of the fittest, so that particles that are more consistent with the measurements are more likely to survive. And as a result, places of high probability will collect more particles and therefore be more representative of the robot's posterior belief. Those particles together, those thousands of particles that are now clustered at a single location, those comprise the approximate belief of the robot as it localizes itself.
Hi, I'm Kathleen, and Sebastian wrote a piece of code for you that I am now going to demonstrate. So the main class is a class called Robot. This robot lives in a two-dimensional world of size 100 meters by 100 meters. It can see 4 different landmarks that are located at the following coordinates: 2020, 8080, 2080, and 8020. So here's how we make such a robot. So it's really easy. All you have to do is call a function robot and assign it to a variable myRobot. So now that we can do things with myRobot. For example, we can set a position. These 3 values are the x-coordinate, the y-coordinate, and the heading in radians. And this command assigns those values to the robot. Let's print these things out. And down here you see the output. X equals 10, y equals 10, and heading equals 0. Next, let's make the robot move. This robot moves 10 meters forward and doesn't turn. So let's print the resulting position. And here we go. You can see that it's now at 20, 10, and 0. It moved 10 meters forward from 10, 10 to 20, 10. Now let's make the robot turn by pi over 2 and move 10 meters. So now the robot is heading in the direction of pi over 2, and it moved forward 10 meters in the y direction instead of the x direction. So as you can tell, it's really easy to program. The last thing I want to show you is how to generate measurements. There is a really easy command called sense. And all it does is give you the distance to the 4 landmarks, 1, 2, 3, and 4. For now, this is all you need to know about the class Robot that Sebastian has programmed for you. You might want to spend some time familiarizing yourself with the code to see how this is all configured.
So thank you, Kathleen. I really appreciate it. This code has a little bit more stuff than you just talked about. It actually simulates noise, but the noise variables are all set to 0. And those noise variables will be important for particle filters, so you can play with those if you like. In fact, there's a function over here called setNoise that allows you to set them. And then later on, we have a function that makes kind of no sense right now, but it will be important as we implement particle filters, called measurement probability. And it accepts a measurement and tells you how plausible this measurement is. This is kind of the key thing for the survival of the fittest rule in particle filters. So if you look through the code, don't be confused by this function. We will actually use it later. So here's our first programming exercise. I'd like you to make a robot that starts at coordinates 30 and 50, and it heads north, which means its heading direction is pi over 2. It then turns clockwise by pi over 2, which means you subtract pi over 2 from the heading direction, and it moves 15 meters. It then senses, and I want you to print out the sensor measurements. It then turns clockwise by pi over 2 again, and moves 10 meters this time. And I just want you to print out the sensor measurements after this entire procedure. So there are two print statements for the sensor over here and the sensor measurements over here. So here's the output I would like your program to generate. After the first motion, the first measurements will be 39 plus something, 46, 39, 46. And then after the second motion, I expect to see 32, 53, 47, 40. Of course, there's lots of decimal point numbers over here, but these are the numbers I would expect you to output. So have fun coding it. And here's my solution. I initialized the robot, my robot, using the function robot. I set the coordinates to be 30, 50, and pi and a half. I then apply the motion command, assign the result to my robot again with minus pi and a half and 15. I print the measurement values. I move again, and I print the measurement values again. And when I hit run, this is exactly what I get. Next, I'd like you to play with the noise. Our class robot has built-in noise variables. One is for forward motion. This is the added Gaussian noise variable to the motion you command. The same for turn, and the same for the sensor measurements. And as I scroll down, I find the function setNoise lets me set those values to values other than 0. So I want you, into your code, set these values as follows. Forward noise equals 5.0, turn noise equals 0.1, and sense noise equals 5.0. So please fit this into your code. And here's how I would do it. I would just call the function setNoise with the parameters as specified for the object my robot. When I hit run now, I get different values, like those, or those, or those. In fact, every single time I hit run, I get a different set of values. So now you know about our class robot, who can turn, and then move straight after the turn, and which also can sense a distance to 4 designated landmarks, L1, L2, L3, and L4. And these distances comprise the measurement vector of the robot. We told you the robot lives in a world of size 100 by 100, and what this means, if this robot falls off one end, it disappears on the other. So it's a cyclic world. So let's now talk about particle filters. The particle filter we're going to program maintains a set of 1,000 random guesses as to where the robot might be. Now I'm not going to draw 1,000 dots here, but let me explain how each of these dots looks like. Each of these dots is a vector which contains an x-coordinate, in this case 38.2, a y-coordinate 12.4, and a heading direction of 0.1, which is the angle at which the robot points relative to the x-axis. So if this robot moves forward, it'll move slightly upwards. In fact, in our code, every time you call the function robot and assign it, say, to a particle, here the ith particle, these elements, pi of x, y, and orientation, which is the same as heading, are initialized at random. So to make a particle set of 1,000 particles, what you have to program is a simple piece of code that assigns 1,000 of those to a list. So let's do this. Let me set n equals 1,000 for 1,000 particles. Here's my initial set of particles. It's going to be an empty list. And I want you to fill in some code after which we have 1,000 particles assigned to this vector over here. So when I print the length of this thing, I will get 1,000 instead of 0. Here's one possible solution. We iterate the following loop 1,000 times. We create an object called robot, and we append this object to our growing list P. And when we're done, we have 1,000 particles. And let me do something I might regret, which is let me just print out this entire set of particles with print P. And what I get is 1,000 items that look just like this over here. If you have an X, a Y, and a heading direction, all generated at random. So if you look through those, you'll find there's a lot of those. So we now have a set of 1,000 particles, each of which just looks like one of these dots over here, and each of which has exactly 3 values associated: an X, a Y, and an orientation. I now want you to take each of these particles and simulate robot motion. Depending on the heading direction, this might yield to different directions. So each of these particles shall first turn by 0.1 and then move by 5 meters. We already implemented something just like this for an individual robot motion. Now I'd like you to apply this to the entire particle set. So please go back to the code and make a new set P that is the result of this specific motion, turning by 0.1 and moving forward by 5.0 to all of those particles in P. So here's one possible solution. We construct P2 as a temporary particle set. We later set P equals P2, so this is just a temporary set. We then go through all the particles again, and here's the tricky line. We append to list P2 the result of our motion of 0.1 and 5.0 applied to the ith particle chosen from the original particle set. So this applies the move command to each of the particles exactly the same way we applied move to the robot motion before. And when we're all done, we reset P equals P2, so we've done the full recursion of applying our motion update to our full particle set. If you've gotten this far, then you got about half of particle filters implemented. Unfortunately, it's the easy half, but the difficult half isn't that much more difficult. Let me explain how the second half works. Suppose our actual robot sits over here, and it measures these exact distances to the landmarks over here. Obviously, there's some measurement noise. That we just model as an added Gaussian with zero mean, meaning that we have a certain chance of being too short or too long, and that probability is governed by a Gaussian. So this process gives us a measurement vector of 4 values of those 4 distances to the landmarks L1 to L4. Now let's consider a particle that hypothesizes the robot coordinates are over here and not over here, and it also hypothesizes a different heading direction. We can then take the measurement vector and apply it to this particle. Obviously, this would be a very poor measurement vector for this specific particle over here. In particular, the measurement vector we would have expected looks more like this. That just makes this specific location really unlikely. In fact, the closer our particle to the correct position, the more likely will be the set of measurements given that position. And now here comes the big trick in particle filters. The mismatch of the actual measurement and the predicted measurement leads to a so-called importance weight that tells us how important that specific particle is. The larger the weight, the more important it is. When we now have many, many different particles and a specific measurement, each of these particles will have a different weight. Some look very plausible, others might look very implausible, as indicated by the size of the circles over here. We now let these particles survive somewhat at random, but the probability of survival will be proportional to their weights. So something has a very big weight like this guy over here will survive at a higher proportion than someone with a really small weight over here. Which means after what's called resampling, which is just a technical term for randomly drawing n new particles from these old ones with replacement in proportion to their importance weight. After that resampling phase, those guys over here very likely live on, in fact many, many times, whereas those guys over here likely have died out. And that's exactly what happened in our movie in the beginning when we looked at localization in this corridor environment. The particles that were very consistent with the sensor measurement survive with a higher probability, and the ones with lower importance weight tended to die out. So we get the fact that the particles cluster around regions of high posterior probability. That is really cool, and all we have to do is we have to implement a method for assigning importance weights, and that is of course related to the likelihood of a measurement, as we will find out, and we have to implement a method for resampling that grabs particles in proportion to those weights. So let's just do this. So let me add back the robot code. We build a robot and we make the robot move. And we now get a sensor measurement for that specific robot using the sense function. So let's just print this out. These are the ranges or distances to the 4 landmarks. And by adding a print my robot statement, we can also figure out where the robot is. Obviously, this is a random output because we randomly initialized the position of the robot. What I want you to program now is a way to assign importance weights to each of the particles in here. I want you to make a list of 1000 elements, where each element in the list contains a number. So this number is proportional to how important that particle is. And to make things easier, I coded for you a function in the class robot called measurement probability. This function accepts a single parameter, the measurement vector, the z I just defined, and it calculates as an output how likely this measurement is. And it uses effectively a Gaussian that measures how far away the predicted measurements would be from the actual measurements. You can dive into this code, understand what's going on. There's one last change we have to do to make this code run. We have to actually assume that there's measurement noise. If there's zero measurement noise, then this function will end up dividing by 0. So let's put in a clause that specifies what we believe the actual measurement noise is. And I'm going to do this not for the robot, but I'll do this for the particles. In this line of code over here, where we create the particles for the first time, I not just initialize these positions with random numbers, but also assume a certain amount of noise that goes with each particle. 0.05 for the translational noise, 0.05 for the rotational noise, and 5.0 for the measurement noise in those ranges. So this is the crucial number over here. So coming back to what I want you to do, I wish you to construct a list of 1000 elements in W, so that each number in this vector reflects the output of the function measurement prob applied to the measurement z that we receive from the real robot, such that when I hit print W, I actually get a list of 1000 importance weights. And this can be done in a single line of code. We construct the list W by appending the output of the function measurement prob applied to the ith particle with the argument of the actual measurement. And as you see over here, most of them look insanely unlikely. So they have exponents of minus 146 or minus 24. Some of them are more likely, the ones that are closer to the truth, like minus 5. Those are the particles that should really survive, whereas those ones over here with a minus 126, those are really ready to die off because they're so far away from the truth, we really don't need them anymore. So in the final step of the particle filter algorithm, we just have to sample particles from P with a probability that is proportional to its corresponding W value. Particles in P that have a large value over here should be drawn more frequently than the ones with a small value over here. How hard can that be? And it turns out it's actually harder than you think, but I'm going to show you how to do it. And once you've done it, you can use the exact same code forever for any particle filter. But let me be precise what resampling actually means. We are given n particles, each of which has 3 values, and there's n of them. And they also now have weights. These are simple floats or continuous values. Let's call big W the sum of all these weights. And let's normalize them just for the consideration of what to do. Let's call the normalized weights alpha. So alpha 1 would be the weight 1 divided by the normalizer W. And so on all the way to alpha n. And obviously, goes without saying that the sum of all alphas is now 1, since we normalized them. What resampling now does, it puts all these particles and their normalized weights into a big bag. And then it draws, with replacement, n new particles by picking each particle with probability alpha. So for example, alpha 2 might be large, so we're going to pick this one, P2. Alpha 3 might also be large, we pick that one. Alpha 4 might be really small, just by chance we might actually pick it, so we have P4 over here. And then we might pick alpha 2 again. So we get 2 versions of P2. Perhaps even 3 versions of P2, depending on the probabilities. We have n particles over here. We do this thing n times, which is, as I said, with replacement, we can draw multiple copies of the same particle. And in the end, those particles that have a high normalized weight alpha over here will occur likely more frequently in the new set over here. That's called resampling. So to make sure you understand this, let me ask you a couple of quizzes. Suppose we have 5 particles with the following importance weights: 0.6, 1.2, 2.4, 0.6, and 1.2. If I, in the process of resampling, randomly draw a particle in accordance to the normalized importance weights, what is the probability of drawing P1, P2, P4, and P5? And the answer is 0.1, 0.2, 0.4, 0.1, and 0.2. And to see, we just have to normalize those importance weights. The sum of those numbers over here is 6. So we divide 0.6 by 6, we get 0.1. 1.2 divided by 6 is 0.2. 2.4 divided by 6 is 0.4. Obviously, those over here add up to 1. So let me make these alpha values explicit and ask you another question. Is it possible that P1 is never sampled in the resampling step? Yes or no? Please just check one. And the answer is yes. In the random resampling process, something with an importance weight of 0.1 is actually quite unlikely to be sampled into the next data set. Let me now ask the same question about P3, which is the particle with the largest importance weight. Please check yes or no. Is it possible that P3 is never sampled in the resampling step? Yes or no? And the answer is yes again. Even though this importance weight over here is large, it could happen that in each of the 5 resampling steps we pick one of the other 4. So I want to ask you a tricky question, and maybe you can calculate this. So what is the probability of never sampling P3? To answer this question, assume we make a new particle set with n equals 5 new particles, where particles are drawn independently and with replacement. And the answer is 0.0777 approximately. And the way to obtain this is, for this particle to never be drawn in the resampling phase, we always have to draw one of the following 4 particles. Those together have a probability of 0.6 to be drawn, which contrasts to the 0.4 for P3. So for 5 independent samplings to draw one of those 4, we get a total probability of 0.6 to the 5th, which is approximately 0.0777. Put differently, there is about a 7.7% chance that this particle over here is missing. But with almost 93% probability, we'll have this particle included. If we had, instead of P3, gone for P1 over here, which has a much smaller probability of being drawn, then the 0.07 will be as large as 0.59, which is 0.9 to the 5th. Now this means with about 60% chance, we will lose particle 1, and only with 40% chance, we will include it. Put differently, the particles with small importance weights will survive at a much lower rate than the ones with larger importance weights, which is exactly what we wish to get from the resampling step. So what I'd like you to do next is to modify our algorithm to take the lists of particles and importance weights, to sample n times with replacement n new particles with a sampling probability proportional to the importance weight. Or in the code, now that we calculated our new particles and the corresponding importance weights, construct a new particle set P3, which we will call P again when everything is said and done, so that the particles in P3 are drawn from P according to the importance weights W. Now to warn you, this is more difficult than it looks like. I'm going to show you a trick in a second, so if you fail to do this, don't worry, I give you a chance to do it right now. But then I'm going to tell you a little bit more about how to organize this in an efficient way, and you get a second chance. So try it out, see if you can do it. And if you fail, look for my advice and then try it again. Now it turns out this is not an easy thing to do. An obvious idea might be to compute all these normalized alphas, but you still have to be able to sample from those. So in the spectrum of all alphas, you might draw a random variable, uniformly from the interval 0 and 1, and then find out the alpha so that all the alphas leading up to it in sum are smaller than beta. But if we add the new alpha to the sum, you will get a value larger than beta. Now that's doable. It's inefficient. In the best case, you get an n log n implementation. Let me show you what is commonly done. And I don't take any guarantee that it's entirely unbiased, but there's a very simple trick. So here's an idea how to make this more efficient. And it turns out empirically it also gives better samples. Let's represent all our particles in importance weight in a big wheel. Each particle occupies a slice that corresponds to its importance weight. Particles with a bigger weight, like W5, occupy more space, whereas particles with a smaller weight occupy less space. Very initially, let's guess a particle index uniformly from the set of all indices. I denote this as a uniform sampler U from the discrete set of choices of index 1 all the way to n. And there's a caveat in Python, of course, it goes from 0 to n minus 1. So say we pick W6. Then the trick is, I'm going to construct a function beta that I initialize with 0, and to which I add, when I construct these particles, a uniformly drawn continuous value that sits between 0 and 2 times W max, which is the largest of the importance weights in the importance set. W5 is the largest, so we're going to add a random value that might be as large as twice W5. Suppose the value we added brings us to here. So this is the value we actually drew, measured from the beginning of the 6th particle we chose in the initialization. I now then iterate the following loop. If the importance weight of the present particle doesn't suffice to reach all the way to beta, so if W index isn't as big as beta, then I subtract from beta this very value W index, and I increment index by 1. So what have I done? I've moved index to over here, and I removed this part of beta. So the point over here is still the same as before. When I now get to the point where beta becomes smaller than W index, which is the case in the next iteration, now index equals 7, then index is the index of the particle I pick in my resampling process. So pick the particle index. I now iterate, I add another uniform value to beta. Say I add this one. This is the value I add, this is the value beta previously had. The same iteration now will make index flop up, reducing beta by all the slice over here, which is W7. It'll then jump over here, and particle 1 is picked. It can easily happen that the uniform value is so small that the same particle is picked twice. And it's easy to see that each particle is now picked in proportion to the total circumference it spans in this wheel of particles. So this is essentially my implementation for the resampling step. So I want you, if you can, implement that specific resampler in Python. So here's my implementation of the resampling step, and it follows the same logic that I gave you in the diagram. We're creating a new set of particles called P3, and it's an empty set in the beginning. And inside this routine, every time I resample, I add a particle from the previous particle set with the index. So that's the main loop over here. And in the end, I assign P3 back to P. So that's the resampling step. My very first index is drawn at random. This is a uniform random sampler of all the indices. And then I have this running variable beta that I set to 0.0. And I cache away the max of the W just to be slightly faster. You don't have to do this. They're coming over here. Doesn't really matter. You could have a max over here. But then I go and produce exactly n particles. And the way I do this, I add to beta a uniform random that is twice as large in maximum in the range as my max weight W. Now, 2 times max weight W would be a very large step, but by adding a random variable that sits between 0 and 1, I have a uniform between 0 and 2 times MW. And then, while this beta variable is larger than the weight of the current index, I subtract this weight from my beta value, and I increment index by 1 modulo n, the total number of particles. And when it's smaller, I'm done. I can just take that particle, add it, append it, and repeat. So this entire procedure over here is somewhat involved. If you got that right, I'm impressed. I hope you learned something from doing it. It happens to be really easy to program once you know what to do. And every time you run a particle filter, you can just reuse it. You never have to think about it again because there's nothing domain specific in this specific procedure over here. So let's run it. If I run it, nothing happens. Turns out empty set. So let me print out the resulting set of particles. So now it has a print P over here. Let me run it. And of course, I'm going to get 1,000 particles, right? A lot of particles. But let me look through them. If we just look at the first value over here, they're now all about the same. They're all between 76 and 82. The second one, they're all about 42, 44, 43, 41, 39, 38. So what we've gotten here is a set of particles that are all co-located. So instead of having a complete random set of particles that we had before, the resampling step, you can see this, already gives me particles with very similar x and y positions. Now it turns out the orientations are not very similar. They're jumped like crazy. And the reason is, well, if you think about it, we only have one location so far. Our distances to landmarks are independent of the orientation. So as a result, orientation plays no role in the projected measurement and therefore has no role in the selection. Let me make the point again. Here's our 4 landmarks and we measure the distances to those. A robot facing this direction has a certain set of distances. A robot facing a different direction, like this one, has the exact same set of distances. Therefore, in our particle filter, the heading direction plays no role. Here's a quiz. Will orientation, or heading, never play a role? And the answers are yes, never. So we always get a random set of orientations. Or no, eventually they matter. And the correct answer is, of course they will eventually matter. So no is the correct answer. And let me show this to you. Again, assume our 4 landmarks and consider a robot facing to the right, this direction. We get a certain set of distances that is invariant to the orientation. But now this robot moves and we get a new set of distances. And now our orientation matters. If we assume a different initial orientation, like this one over here, and that robot moves, its measurements would be very, very different. So orientation does matter in the second step of particle filtering because the prediction is so different for different orientations. Let's go and program this. So I want you to take this particle filter and program it to run twice. And here's my answer. This is all initialization over here, so we shouldn't touch it. But from here on, we want to do things twice. So we're going to put a for loop here from t in range t. And then we have to indent all the stuff below. I indent all the way to the final statement, but I only want to print the final distribution. Let's run it. And surprisingly, the orientations aren't really that well worked out. If I go down, I find still fairly random orientations here. But if I go to 10 steps forward, which means the robot really moves quite a bit across its environment, and I hit the run button, I actually get orientations that all look alike. So you can see they're all about 3.6, 3.8, 3.9, 3.7. You can see the y values are all about the same. And the x values are all about the same. So this is the particle filter working. What I do next is to give you another programming assignment. Rather than printing out the particles themselves, I want you to print out the overall quality of the solution. And to do this, I've programmed for you an eval code, which takes in as a robot position and a particle set, and it computes the average error of each particle relative to the robot pose in x and y, not in the orientation. And the way it does it, it basically compares the x of the particle with the x of the robot, computes the Euclidean distance of these differences, and averages all of those. So it sums them all up and then averages them through the number of particles over here, which is upper caps N. Now, there's some funny stuff over here. The reason is the world is cyclic. And it might be that the robot is at 0.0 or at 99.9. These are about the same values, but according to this calculation over here, they'll be different. So by this normalization over here, I make sure that the cyclicity of the world doesn't really affect negatively the estimated error if I'm close to the boundary. You might parse this. I'm adding world size over to the computer model operation and then subtract the same thing over here. Be it as it is, I want you to take the function eval and produce a sequence of performance evaluations. And when you hit the run button, I want you to produce something like the stuff over here. 4.9, 3.6, 2.9, 2.8, 3.1. This is the residual error. Remember, it's a world of size 100 by 100, so this is actually a relatively small error compared to the world size. Can you code it so I get for each iteration the error number produced by this routine over here? So here's my solution. It's a simple command as print eval my robot p. I know it wasn't very hard, but it gets you kind of fun to play with it. So here's a sequence of numbers I get out. It turns out we don't always get the same number. Sometimes it doesn't work. Here's a second run. These are small values again. Another run. Another run. It is a good run. So the error is down to 6 compared to whatever it would be if we didn't do particle filters and had a random set of particles. In fact, to understand this, let me just take the print eval command and move it to the very beginning where we've done no particle filters. So hit run. And what you'll find is it goes from 38 in just one step of particle filtering, which is a drastic reduction of error. Now, run it many times. There will be cases where it fails, where there's no particle nearby. Strangely, they don't show up right now, but when I was testing it and programming it, I actually got one of those. I had an error of like 15 or 20. Whenever I want to demo something, it just doesn't work. Well, this particle filter is just too good. It just gets the answer relatively right really, really quickly. So one thing I want to stress here is that you've just programmed a full particle filter. So you got from me kind of a very primitive and rudimentary robot simulator that uses landmarks as a way of doing measurements, and it uses three-dimensional robot coordinates, so it's a little bit better than the stuff we talked about in previous classes. It's not quite a Google car yet. And you solved the estimation problem. In fact, you solved this problem in 30 lines of code. That is an amazing small amount of code for something that's amazingly powerful. And you can reuse these 30 lines of code in pretty much all problems you might study that require particle filtering. They're very generic. So let me get back to the theory of particle filtering. And let me ask you a few questions. We had measurement updates and motion updates. In the measurement update, we computed posterior over state given a measurement. And there was proportional to, up to normalization, of the probability of the measurement given the state times p of the state itself. In the motion update, we compute a posterior over distribution one time step later, and that is the convolution of the transition probability times my prior. Now those formulas should look familiar. This is exactly what you implemented. You might not know you implemented this. Let me explain to you how you implemented it. This distribution was your set of particles. 1,000 particles together represented your prior x. These were your importance weight. And technically speaking, the particles with the importance weights are a representation of distribution, but we wanted to get rid of the importance weights. So by resampling, we worked the importance weight back into the set of particles, so the resulting particles, the ones over here, would represent the correct posterior. You've implemented this. I'm just telling you what the math is behind this. This you also implemented. This was your set of particles again, and you sampled from the sum by taking a random particle over here and applying the motion model with a noise model to generate a random particle x prime. As a result, you get a new particle set that is the correct distribution after the robot motion. So you recognize the math, and hopefully you understand how your code implements this math. You can prove all kinds of interesting facts about this math. For example, you can prove convergence if the number of particles goes to infinity. It's obviously approximate. Particles are not an exact representation. And it was amazingly easy to program. So when you go over your particle code, you realize you implemented a fairly involved piece of math that is actually the same for all the filters we talked about so far. The same math underlies our histogram filter we talked about in class number 1, and the same math for Gaussians is the Kalman filter we talked in class number 2. So let me ask you an interesting question. Which of the 3 filters did Sebastian use in his job talk at Stanford? Histogram filters, Kalman filters, particle filters, or none of the above? Check one or all that apply. And of course, you can't really know unless you Google me and look at my homepage. Then you might find out some evidence. So just take a random guess and I tell you the answer in a second. I should say I was hired by Stanford in 2003 into a tenured associate professor position. So obviously my job talk wasn't that bad. And the answer are those 2. Those I used in a job talk in 2003. But had previously applied at Stanford and actually received an offer which I turned down in 1998. And in my earlier work, I didn't understand particle filters and did everything with this filter over here. But came 2003, I was a big fan of particle filters. And my job talk talked about a version of those that applied them to the somewhat more involved robot mapping problem. Now fast forward to 2012, we built the Google car. We're now using multiple methods. We use histogram methods and particle methods. The main difference to what you've learned so far is twofold. The main difference to what you learned so far is the robot model. The vehicle is actually modeled as a system with 2 non-steerable wheels and 2 steerable wheels. That's often called a bicycle model because half of it, this thing over here, acts like a bicycle. A big difference is the sensor data. Instead of using landmarks, we give this really elaborate roadmap, and then we take a single snapshot and we match that snapshot into the map. And the better the match, the higher the score. And then on top of it, we have additional sensors, like GPS. We also have inertial sensors. And I'm not going to go into those at all, but the methods I taught you are rich enough to handle these additional sensors. So you've just learned about the gist of the method in which the Google car is able to understand where it is and where other cars are. When you build a system, you have to dive into these more elaborate methods, but I think it's very much doable. It's very easy to replace the current simple motion model with a slightly more sophisticated for what's called a bicycle model, and it's easy to write a correlation function that goes into map data and computes normalized correlations of measurement images and a big pixel map. I leave this as an exercise, so if you want to hack your own car and make it drive itself, have fun. I just want to congratulate you. You've actually, in these 3 classes, learned pretty much as much as any of my Stanford student learns in my specialized AI classes on robotics when it comes to robot perception. In fact, you've learned pretty much what there is to know to become a successful practitioner in robotics. In the next class, I will tell you about robot motion, how to make the robot move. So you're going to move beyond the idea of just state estimation, finding out where we are or where the other cars are, and we're going to move into the fascinating topic, how to use all this to decide where to move. So in the next class, I'll talk about a basic AI method called search. In particular, A-star search, which is an algorithm invented by my colleague Nils Nilsson at Stanford. And I will apply it to the problem of planning robot trajectories and making it move in real time. So I'll see you in the next class.